Okay, what we want to do today is we just want to solve a mole-to-mole stoichiometry problem. So I have a question up here that asks us to calculate the number of moles of CO2 produced from the combustion of 8.00 moles of butane, which is C4H10, in an excess of oxygen. Now, you have to have, first, a balanced chemical equation if you're going to solve this problem, because it's the only way that we can understand how many moles of CO2 we have to moles of butane. So we need to write out our combustion equation. Now, most of the time, these questions are associated with a balanced chemical equation, but oftentimes, if they're not, it's quite easy for you to go ahead and write out and balance the equation. So the combustion of butane, that is C4H10 plus oxygen, because this is a combustion reaction, yields carbon dioxide and water. And so we go back through here and we balance the equation, and for the sake of time, we'll go ahead and just balance this real quick for you so we can get the correct mole ratios. It's going to be a 2, a 13, an 8, and a 10 right here. So our mole ratios are 2 moles of butane to 13 moles of oxygen, resulting in 8 moles of CO2 and 10 moles of water. All right, so let's go ahead and solve this problem. This one here is pretty straightforward. This is just moles to moles. So what we're going to do is we're going to start with our given value here. We have 8 moles of butane. That's C4H10. And that's right here in the balanced equation. And we want to convert this to moles of carbon dioxide produced. Now this part right here, in an excess of oxygen, don't let that trip you up too much. That's just basically saying we have enough oxygen for all of our butane to react. So we know that all 8 moles of butane will react and result in a certain volume or a certain amount of CO2. So this is just a one-step dimensional analysis problem. We'll go ahead and set up our dimensional analysis, and we want to put the unit moles of butane down here on the bottom because we want to cross it out at the end. And we want to convert to moles of CO2, and so we're going to put that in the top, moles of CO2. So for this, we need the balanced chemical equation up here. We can see that the equation tells us that we will use 2 moles of butane to produce 8 moles of CO2, and those are the numbers that go here. 2 moles of butane will produce 8 moles of CO2. We can use a different color if we want to make that better here. We have the pink here, 8. Okay, 8. So we're ready to solve our problem because we have converted from moles of butane to moles of CO2. Okay, so we're going to bring up our calculator. Let's move it over here so we can, well, it's kind of in the way anyways, that's all right. So let's clear out some old math we had there. Now, what we're going to do here is 8 times 8, oops, lost our calculator, 8 times 8 divided by 2. So 8 times 8 is 64, and then divided by 2 gives us 32. So we have 32 moles of CO2. And the last thing we'll do here is we need to make sure we have the correct number of significant figures. These are counted numbers here, the 8 and the 2. They're exact numbers, so that they have an infinite number of significant figures. They don't really count for our final count here. This number here, 8.00, has 3 significant figures. So for our answer to have 3 significant figures, we're going to have to add a 0 after the decimal here. So 32.0 moles of CO2, which will give us 3 significant figures. Okay, so in this next question, it says to calculate the number of moles of butane required to combust in an excess of oxygen to produce 12.5 moles of water. So this is going to be solved much the same way. Here, again, don't get too caught up on the excess of oxygen. It just means we have enough oxygen, and we want to know if we have enough oxygen, how much butane is it going to take to produce 12.5 moles of water. So nothing different on how we solve it. We have 12.50 moles of H2O, and to convert this correctly, we need the balanced equation again. So we see the balanced equation tells us that 10 moles of water are produced for every 2 moles of butane burned. And so that's what we're going to put down here. 10 moles of water produced for every 2 moles of butane that combusts. And we know to put moles of water on the bottom because our unit of up here is moles of water, and that's the only way at the end that those two units will cancel. We'll be left with just the unit of the answer that we want. So we have 12.5 times 2 divided by 10. So we bring up our calculator. We'll have 12.5 times 2, so that's 25, divided by 10. And of course, dividing by 10 just moves the decimal over to 2.5. So our answer is 2.5 moles of butane. Now, again, we go back to our starting number here, and we see that we have 4 significant figures. So we need to make sure our answer also has 4 significant figures. And if you see here, 2.5 is only 2 significant figures. And so the best way to gain some significant figures here is to just put some zeros after this 5, because it's to the right of the decimal and to the right of a non-zero digit. And so it will be significant. We would say 2.500 moles of butane, C4H10.